your Alex trig chart available to you. We're going to do at least one problem of each type of this. And Jeremy, if something looks weird to you on that, just let me know. Hit the pause button. All right, does everybody have the questions? Who has paper? You don't really need a calculator for this. All right, let's get going. Are we recording?
Yes.
Yeah, oh, well, in case. Thanks for joining us. Hi, John. Sorry. Subscribe joke. So here we go. Prove the identity. Tangent cubed x times secant to the fifth x equals quantity secant to the 6x minus secant to the fourth x times secant x tangent x. Now, I don't know about you, but in this case, the right-hand side looks a little more complicated than the left-hand side. All right, but anyway, as always, we will start with the left-hand side and see what we can do with that. So on your paper, we're going to write tangent cubed x, secant to the fifth x. All right. Now, if you look on your Alex trig chart, you won't see anything with tangent cubed, or anything cubed for that matter, or to the fifth. So over here, Mr. Goddard's trig tips and tricks. I would recommend that anytime you have something to the third, or maybe even higher than that, we'll say if you have anything to the third, sometimes, not always, you want to turn that into anything squared times anything. The reason being is we have quite a lot of formulas and identities that deal with something squared, or anything squared, but not any dealing with the cube. So we'll kind of use that as our basis here. We'll turn that tangent cubed into a tangent squared x times the tangent x times the secant to the fifth x. So, somebody looking at the trig chart, do we have a tangent squared anywhere on there?
No.
Let's look at the Alex trig chart. There might be tangent squared. Tangent squared plus 1, but let's find the one that just has tangent squared itself.
Secant squared x minus 1.
Secant squared x minus 1. Okay. Tangent x secant to the fifth. Oh, I'm falling behind here. That first step was algebra. This step, I believe, is Pythagorean identity. Now we're getting somewhere. Remember, another one of my tips and tricks is always kind of keep the end in mind. Always kind of look and see. That's got a minus there. Now I've got something with the minus looking pretty good. What we're going to do now is we're going to take this entire two terms, which are multiplied by that, and we're going to distribute all of them times the secant squared x and all of them to that minus 1. Okay? So this is going to equal tangent x times secant to the fifth x times secant squared x, which turns into a secant to the seventh x, minus tangent x secant to the fifth x times 1. So that's just tangent x secant to the fifth x via algebra. All right, so always keeping the end in mind here, looking at this, looking at that. I'm looking at some powers here, a 7 and a 5, and over there I'm seeing a 6 and a 4. Also, it kind of looks like maybe they, this has been factored out, a secant x and a tangent x has been sort of factored out of that. And that's exactly what happened. Notice if we have both these terms, we have a tangent x, so I can factor out a tangent x. It looks like I can also factor out a secant x. Now, truth be told, you could actually factor out a secant to the 5th x and be left with secant squared and just nothing over here. But according to where they want us to go, we're only going to factor out a secant x. When I do that, when I divide this by the tangent secant, I'm left with a secant to the 6th x. And when I factor those terms out of this term right here, I'm just left with the secant to the 4th x. And that's exactly where we're going. That's the right-hand side. So I guess another trick or tip, factor sometimes. Factoring is a thing that you need to think of. It's another tool in your toolkit for solving these problems. Anybody have a question about number 1? All right. We'll give you about maybe 2 or 3 minutes. See if you can make some progress there as a table on number 2. Where we have sine cubed x times cosine cubed x equals cosine cubed x minus cosine of 5th x times sine x. So while I take attendance, see if you can take care of that one.
Cosine to the 4th. What? Yes. No. Because there's also another cosine. No. It'd be cosine to the 4th. No. Because we have. Oh no, we only have one.
Oh, okay.
So I'm saying cosine squared. And then it's times cosine squared is 1 minus.
Alright, so the reason why we split those cubed into a square times a single is so that we convert those squared into something like Pythagorean.
Skip stuff.
Ongoing on?
Oh, that's mine. Thank you.
Also another one there.
I don't know who that was.
I guess we'll leave it there. Ooh, good. Use the Pythagorean identity. Now this is getting kind of a little bit crazy over here now.
Yeah, I'm a little stuck now.
Yeah. I'll tell you what though, let's keep the end in mind. Where are we going with all of this?
Okay, so we want
I'm looking at this and I'm seeing a lot of cosines.
Okay.
You know what I'm saying? So maybe let's leave that cosine alone.
Or leave it as cosine.
Yeah, I'd leave it as cosine cubed because we've got a bunch of cosines here. So yeah, in case y'all are just tuning in, several of you were splitting that sine cubed up into a sine squared times a sine single. Yeah, that's a great idea. I also noticed you were splitting up that cosine cubed, but that's going to get kind of crazy. And hopefully you can kind of see if you look down the line, that's sort of in your mind. That's not going to go where we want to go. Leave that. Let's leave that cosine cubed all by itself.
Step on top.
All right.
I'm going to keep going.
No. Who's got an idea on what to do now?
Hold on.
Yeah, let's distribute that. I'm going to circle everything needs to be distributed. We're going to distribute it to the one and distribute it to that guy right
So the
there.
sine x, cosine cubed x, that's all one term, right?
Exactly, because it's being multiplied. Yeah. You normally aren't used to seeing two things on the outside that are multiplied. You're normally just used to seeing one of them. But if this one's getting times two, then or multiplied as well, then it all has to go in. It's all of this times that. So it has to be times there and times there. Does that make sense? Annie, you got a question? I know you do.
Oh, I figured it out. I mean, you figured it out.
Okay.
You don't
It's weird. It's weird seeing two things on the outside. Is that what you're?
Yeah, and I was confused how you like multiply the sine times
Cosine, yeah, me too. But since they're two different ones, nothing really happens to it when you times it by cosine. But
Yeah.
something happens to the cosine.
It's literally this times this times this, and the cosine cubed times cosine squared can be simplified to
Right.
cosine to the fifth.
Yeah, and when you say it like that, it makes super sense.
So, all right. Suggestions on what next?
Factor out sine.
Yeah,
And
factor
cosine.
out. Let's see where we're going here. According to this, it looks like they just pulled out one sign. Is it now? It is totally possible to factor out a cosine cube from both of those terms, which I would say is normally the best thing to do, is to factor out your the greatest common factor. But they chose not to. They just want you to factor out a sign. Three and five. Pretty nice.
Do we have to draw that line between
I
what
just,
you're solving and
no, I just did that to show you. All right, let's look at number 3 and brainstorm some ideas. I don't know if we need to do it all the way entirely, but let's talk about number 3 and all of its weirdness. Sine to the 7th.
sine squared times sine to the fifth.
Okay, I hear a sine squared times sine to the 5th. I'm just going to sort of just sketch some ideas here. Sine squared x times sine to the 5th. If we do that, where would we go next?
1 minus cosine squared.
Okay, so I replace that with 1 minus cosine squared x. Then what?
And distribute the sine 5x to the
Okay, let me stop you right there though, because this actually looks really close to this final answer. If we start distributing though, then it's going to kind of deviate. It's practically in the form right there that it is. I just need to get a 3 up here, and I need this guy to drop down to like a 1. So let's do the same thing to this sine to the 5th that we did to the sine to the 7th.
And make it a 3 and a 2.
Yeah. So we got 1 minus cosine squared. Let's turn this into a sine squared x times a sine cubed x, right? Tell you what though, let me do one more. Let me write it like this. Sine squared x times sine squared x times sine x. A 2, and a 1. Right? Because I mean, anytime you're multiplying things together, you just, if they have the same base, then the exponents would add. The advantage here is this would be sine squared can be turned into 1 minus cosine squared. Sine squared can be turned into 1 minus cosine squared. And the sine x stays. And then notice I have 1 minus cosine squared, 1 minus cosine squared, 1 minus cosine squared. And so that would be 1 minus cosine squared x cubed.
of 1 minus cosine.
You would have to, yeah. Now, the only reason why we went this way is because that's what you suggested first, and I decided to chase that. A simpler way, but it's kind of hard to know it's very hard to optimize something from the very beginning. The normal way of doing something is to do it the long way or do it the way that you understand, and then go back and see if you can optimize it. The way of optimizing this would be to turn that sine sub x into a sine x times sine squared x cubed. This is the ultimate optimization here, because squared time when you have a power of a power, then that's 6. You multiply those two, and so then you would just do one more step. That's 1 minus cosine squared x cubed times sine x. So you could do this in 2 steps rather than several. But I have found that when teachers, math teachers especially, do optimum steps in front of the class, you don't really get it, because it's not the way you're thinking. You're kind of thinking like this, trial and error, figure it out, and so it's better for us to just use the ink. Okay, all 3 of those are actually the same type of problem. It's something with the algebra, something with Pythagorean identities. These next 3 problems, excuse me, are a little bit different. And they're going to be utilizing the sum and difference formula that's on your oldie goldie trig chart, but not on that handy dandy Alex trig chart. So let's go ahead and look at number 4 here. Cosine x minus y times sine x minus sine x minus y cosine x. Do y'all remember the sum and difference formulas? Sine u plus v, cosine u plus v. They're on the bottom left corner of your trig chart. And that's what we've got right here. We've got a cosine x minus y. We have a sine x minus y. Sort of like a u and a v situation. So let's go ahead and simplify that. Let's expand it all out. I'm not going to write the formula down anymore. Y'all are beyond that. So, Michaela, call out to me the cosine u minus v formula, but instead of saying u, say x. Instead of saying v, say y.
Okay, so cosine x cosine y plus sine x sine y.
Are we in agreement, class?
Yeah.
I am in agreement as well. So, that whole item right there has been replaced with this whole item right here. All of that is being multiplied by sine x. And then this one, sine x minus y. Janie, go ahead and find that formula, sine x, or sine u minus v. Call it out to us, but instead of saying u, say x. Instead of saying v, say y.
So sine x cosine y, and then it's minus cosine x sine y.
Are we in agreement, class? Mostly we want to check to make sure your minuses and pluses are correct. Those look correct to me. Okay, try to do the color code there to help you all out. Oh, in Alex, for this problem set, and you look over on the justification reasons, there will be a new reason that will show up. It'll say sum and difference. That'll be one of the options.
Could we have done it all in one step on Alex, or do we have to do it in 2 steps?
You can do it all in one step. Since it's the same substitution.
Okay.
Next thing we're going to do is distribute. So sine x times cosine x cosine y. Plus sine x times sine x times sine y. Now sine x times sine x we can combine to form sine squared x times sine y. And over here, I've got a leading minus cosine times cosine y, so I'll write that as sine first when I have the option. Sine x, cosine x, cosine y. There's a minus out front, but there's a minus in the middle, so those two will cancel and form a positive. I have cosine times cosine, which is cosine squared x, times the sine y, also known as sine.
Now, can you cancel out sine x, cosine x, and cosine y?
Mm-hmm. Because that term right there, sine x cosine, is subtracted right here. So now I have a sine squared x times sine plus a cosine squared x times sine. Anyone have a suggestion on what to do next? We could, but we're not going to. Not quite yet. You can't do, you're suggesting maybe turn this into a 1 minus cosine squared? That is a possibility, but there's something that I'm noticing that's similar about both of these.
Combine them or add them.
They both have a signing, that's right. So we're going to factor out the signing. And the only reason I said no to that is because, for the sake of time, I want to make sure we get through all these problems. When you're actually doing your homework, you might not really know. But if you look at it, you do one step here, and I mean, actually, you'd have 1 minus cosine squared, and then that whole term would cancel. You'd be fine. You actually would probably get to where we're going. But now, your Pythagorean identity, sine squared plus cosine squared is? That's right, it's 1.
Oh.
So we're just left with signing, which is where we're going. Any other questions? Somebody else, question?
So sine squared x plus cosine squared x to each one.
So saith Pythagoras. All right, number 4 looks pretty good. Number 5 looks very similar. 6 looks similar. Let's go ahead and look at number 7. Because that's got some numbers in it.
That's fractions.
Yeah. Cosine pi over 2 plus x divided by cosine pi plus x. think one of those somewhat resembles the what do they call it? It's the co-function identities or something like that. Yeah, co-function. But we're not going to mess with that. I'll just say right now, everything we're dealing with in this particular homework is sum and difference, as well as we'll see the last two problems with double angle formulas. So we want to attack this from a double angle formula perspective, where this is U and that's V. Well, I hope you brought enough for everyone. Hi, John. You can take those headphones out too. All right. Who wants to play? Ravi. Find that cosine formula. Replace the u with pi over 2. Replace the v with x.
Which one are we using?
It's going to be the cosine u plus v.
Cosine pi over 2 cosine x minus sine pi over 2 sine.
Class, are we in agreement with her pluses, minuses, and signs? I'll rely on y'all. I'm going to answer it right here. And then we have cosine pi plus x, very similar kind of thing. Stephanie, you read that one too, as the formula out, and only instead of saying u, say pi, instead of saying v, say x.
Cosine pi. Cosine x. Minus sine pi sine
See, don't that colors help out so much? All right, class, we love cosine pi over 2. Why do we love cosine pi over 2, Jeremy?
Because it's 0.
Because it's 0. It's on that unit circle. I'll put in parentheses so you can understand that I'm evaluating it. So 0 times cosine x minus, Rosa, Nick, sine pi over 2. I'm sorry, say again? It is 1 when you evaluate it. Yep. Anybody? Cosine pi? That means look at the x value on pi. Pi radians.
Negative 1.
Just a little louder. Negative 1 times cosine x, that stays the same. And keep talking to me, sine pi. Uh-oh. Slacking here. Reasons. Reason here, sum and difference formula. We'll just say sum and difference. What do you think the reason would be here on this step where we are evaluating those values? Just pick a guess, Rosa. It's not quite algebra because we're at, that normally means you're moving letters around and stuff like that. Trig would be somewhat appropriate because we are using trig knowledge, but we're technically evaluating whatever those are. So the correct term that Alex is going to give you now is evaluation. Sorry, I was trying to give you little hints there. All right. So 0 times cosine, that's gone. So this is just going to be a minus sine x minus cosine x minus 0. So multiplying stuff like that, that's algebra apparently. I would say that's evaluation too, but whatever. Negative over negative, they cancel out. Sine over cosine is tangent. found that the longest way round is the shortest way home. Back to tangent.
Why did Barry say negative? Oh, never mind.
Okay, number 8 looks very similar. You're going to have sum and difference formula. Number 9, you'll utilize the sum and difference formula with tangent. Number 10.
Yeah.
There's also actually an 11 and 12 that were kind of cut off.
Oh no.
Because I didn't print them. So we might do number 12. Yeah. After we do number 10. We got time. Alright, let's do this. There's something different about number 10 that we haven't seen before.
Do we?
We do have a cosecant. Normally we don't write the cosecant, but there's something even stranger than just the cosecant.
Do you make the 1 minus sine squared x back into cosine?
Yeah, we're probably going to do that. You're kind of thinking on the left-hand side. What I want you to notice is that inside this cosecant, it's 2x. Meanwhile, all over here we have single x's. Okay? Here we've got cosecant of 2x. So these last few problems are going to be utilizing the double angle formula. It's on the right column on your oldie goldie trig chart called the double angle formulas. So keep that in mind. Also, y'all remember what cosecant is in the reciprocal identity? It's 1 over
Sine.
1 over sine. So that's going to be 1 over sine of 2x. It's whatever's inside the parentheses, it's got to be the same. And since we're talking about it, and looking at that double angle formula, what is the sine of 2x, class? I think it's on your paper it says the sine of 2u. Yeah. What's sine to u? Well, it's 2 sine u cosine u. In this case, 2 sine x cosine x. Kind of weird. We never really think like this in terms of like working your way backwards, you know, rather than starting our way forwards or whatever. But if you've ever solved a maze and gotten kind of lost as you're starting to go through, y'all ever do that?
Yeah.
You're like, I'm trying to fill the maze. Oh wait, I don't know where I'm going. And so then you skip to the end, and then you kind of work your way backwards a little bit. Yeah, that's kind of what we're going to be doing here. We just did it. We kind of worked our way backwards, and so we're like, okay, if I can get to this point over here, then I know how to get the rest of the way. And that's a good way of solving puzzles, and it's a good way of solving trig proofs. So here we go. Let's start with the left-hand side. 1 over 2 tangent x times 1 minus sine squared x. Janie already suggested that we replace the 1 minus sine squared x with cosine squared x using the Pythagorean identity. I'm now open to suggestions on what to do next.
In a case like this, do we need to put everything in sine and cosine?
I think that's a good idea.
So tangent into sine over cosine.
Yep, let's turn that tangent into sine over cosine. Utilizing the quotient identity. And then you just start seeing this. You're like, got this, I got this. Cosine denominator, cosine numerator. Those cancel. So that's 2 times the sine times the cosine. And then you're like, aha!
There we are.
We made it. We made it to that midway point. So we know how to get the rest of the way home now. 2 sine x cosine x is the sine of 2x utilizing the double angle formula. Alex will just give you the option of writing double angle. That's an angle. And then 1 over sine 2x using the reciprocal identities is cosecant of 2x. I guess it wasn't that difficult. Are you ready for the last problem that I will demonstrate in front of all of you for the semester? I think you're ready. We're gonna go full on sloppy on this one. All right, we're just gonna. I'm not even gonna do a formal proof. Here we go. Prove this. Secant squared of 2x over 2 tangent x equals cosecant of 2x. Oh, hold on. Just secant squared x, thank you. All right. What do you notice about this one in similarity to the last one? We still have this like cosecant 2x, right? We're like, hey, we know that. We know that that one is 1 over sine of 2x, right? Which we just saw a minute ago is equal to 1 over 2 sine x cosine x. This is the way I'm going to prove this one. So, since this is going to be super informal, we can do multiple things at one time. Let's turn that secant squared into a
Tangent.
1 over cosine squared x. Using the quotient, I'm not even going to write the justification. Y'all know it. 2 tangent x, I'm going to write that as 2 times sine over cosine. Oh no, what do I do now? Fraction of fractions.
Multiply by others.
Multiply by reciprocal. Alright. So this is going to turn into 1 over cosine squared x times, we'll kind of put that 2 in the numerator there, cosine squared x divided by 2 sine x. Hold on. Something's wrong here. This cosine over here is squared. This first one here is, that's just regular cosine. This cosine is one of those. So I've got 1 over 2 sine x cosine x. Hooray! Which gets me there, which gets me there, which gets me there. No. I'm clapping for you. All right. Now all you have to do is demonstrate that you can do this on your own. We have a work day tomorrow.
Yes. I love working.
A short-term knowledge check on Friday and a whole pie chart knowledge check on next Tuesday. I didn't think you could look anymore.
You are
Short-term knowledge check on Friday. That's a review knowledge check. And a cumulative, that means our buddy, pie chart.
Yeah. He got that.
Something like that.
The same question.
I think we had like maybe
Right.
three,
Right.
we got like 4 so far maybe. 3 first 9 weeks. This will be our second one for this 9 weeks.
I made one for you.
Michaela, you can stop the